13.8 billion years ago, everything we call reality appeared. Space, time, matter, energy, and the very rules that hold the world together. But the harder we stare at that first instant, the shakier our everyday language becomes. What does it even mean to ask what came before? If before is a word built by time itself. At the boundary physicists label T0, our equations throw up infinities, our metaphors run out of air. Still, science offers disciplined ways to approach the question, not with final answers, but with testable ideas that respect the evidence we have, from quantum foam to inflation, from cyclic bounces to holographic hints, from the arrow of time to the role of observers. Each path illuminates a different facet of the mystery. We'll walk these paths carefully, separating what is measured from what is proposed, and ending each step with a simple question that carries us forward. What counts as a beginning? Reframing the problem. Everyday time is a line. Physics complicates that picture. In general relativity, time is woven with space into a curved, dynamical fabric. In quantum theory, events appear as probabilities that only settle into definite outcomes when interactions make records. Press both theories toward T0, and mathematical divergences appear, signaling the limits of our current tools rather than a failure of nature. The key move is conceptual. Replace what happened earlier with how could the stage on which earlier and later make sense come into being. That pivot doesn't dodge the question, it makes it precise, and it suggests a research program. Look for mechanisms that generate time as a measurable quantity, explain large-scale smoothness and flatness, seed the right spectrum of primordial ripples, and make at least one prediction we can try to catch with instruments. If a model cannot do that, it belongs to the philosophy shelf, not the lab bench. So, where do we begin? The Planck frontier, where our best theories talk past each other, run the cosmic clock backward. Temperatures soar, density spike, and at about 10⁻⁴ seconds, the Planck time, the very notion of a smooth space-time, likely breaks down. Below the Planck length, the fabric should look more like a restless sea than a continuous sheet. General relativity is superb where space-time is smooth. Quantum theory rules where discreteness and fluctuations matter. We need a single framework where both are true. That is why so many proposals, string theory, loop quantum gravity, asymptotic safety, causal sets, aim at the same bottleneck, a mathematically consistent description of geometry when quantum uncertainty cannot be ignored. Until then, what happened at T0 remains a question we can only approach obliquely by studying signatures left slightly after it. Those signatures are our compass. Quantum foam. When emptiness has structure, quantum mechanics tells us that nothing is never truly empty. On short timescales and tiny distances, fields fluctuate, particle-antiparticle pairs flicker in and out. If one imagines space-time as an elastic sheet, the quantum vacuum is a microscopic sea of jitters. It is tempting to suppose that a fluctuation could seed a universe, but almost all such fluctuations are fleeting. A lasting universe would require a driver that amplifies a microscopic spark into a macroscopic domain. The search for such a driver leads to one of the most powerful ideas in modern cosmology. Cosmic inflation, a flash that reshaped everything. Inflation proposes that, a sliver of a second after the notional beginning, a special energy state caused space to expand at an extraordinary rate. In an instant, a region smaller than a proton stretches to cosmic size. That simple mechanism neatly addresses several puzzles at once. Why the universe looks so uniform across vast distances, why space is so nearly flat, and how minuscule quantum jitters could become the seeds of galaxies. Inflation is not a story about creation from nothing. It is a story about how an already existing patch became smooth and big fast. The details, what field drove it, how it started, and how it ended, are under active study. But the broad idea has a crucial virtue. It makes statistical predictions we can confront with the sky. Reheating and the birth of familiar matter. If inflation happened, it had to end. When it did, the energy-driving expansion likely converted into a hot bath of particles, a process often called reheating. That is how the familiar cosmic soup of protons, electrons, and photons could have arisen. The thermal history that followed, nuclei forming minutes later, atoms forming hundreds of thousands of years later, left fingerprints we can measure today, especially in the cosmic microwave background, CMB. Matching these fingerprints is one of the most stringent tests of any early universe model. The overall message is sober. The universe remembers its childhood in detail, and it is willing to share if we listen carefully. Testing inflation. Ripples in the oldest light. The CMB is the afterglow of the hot early universe, cooled and stretched by expansion until it now glows as microwaves from every direction. Its tiny temperature variations map the primordial ripples that later grew into galaxies. Inflation predicts a distinctive pattern in those ripples, nearly scale-invariant fluctuations with subtle departures from perfect uniformity. It also allows for a background of primordial gravitational waves that would twist the polarization of the CMB in a characteristic way. Instruments on the ground, on balloons, and in space have been chasing those signals. The hunt is ongoing, and the result will matter. A detection would sharply favor inflationary pictures. A strong upper limit trims the space of viable models. Either way, evidence tightens the net. Eternal inflation and the multiverse. A landscape, not a single meadow. In many versions of inflation, the process never entirely stops. It ends locally, creating bubbles where regular expansion takes over, while inflation continues elsewhere. The picture that emerges is a vast, possibly unending mosaic of domains with slightly different physical details. Our observable universe would then be one bubble among many. This framework can naturally accommodate fine-tuning puzzles by selection. Only those bubbles with life-friendly conditions host observers who wonder why conditions look tuned. However, we should be frank. Directly observing other bubbles seems out of reach. The measure problem of assigning probabilities in an infinite mosaic is unsolved, and we must resist promoting a useful framing into a claimed fact. The responsible stance is modesty. Explore indirect tests and keep the logic clean. Cyclic and ekpyrotic ideas. Before the beginning, another act. A very different class of models suggests that our Big Bang was not the absolute beginning but a transition, a bounce from an earlier phase. In ekpyrotic scenarios, a long, ultra-smooth contraction precedes a bounce into expansion, ironing out irregularities without inflation. In some higher dimensional pictures, three-dimensional brains drift in a larger space. When they collide, the energy of collision becomes a hot, expanding universe. These models aim to explain smoothness and structure while offering an alternative to inflation's superfast stretch. Their challenges include building a fully stable, non-singular bounce and matching the observed spectrum of primordial ripples. The tests are the same. Predict a pattern, then ask the sky. Loop quantum cosmology. Geometry learns to quanticize. Loop quantum gravity attempts to quantize geometry itself. In loop quantum cosmology, that quantization can make gravity effectively repulsive at extremely high densities, replacing a singular bang with a bounce. The universe would have had a contracting phase, reached a minimum volume where quantum geometry dominates and then expanded. This delivers a clean answer to the singularity problem, but it raises others. What were the conditions in the prior phase? How do we carry information across the bounds? And do the statistical predictions match the CMB? The promise is conceptual clarity. No infinities at T0. The hurdle is empirical, numbers must line up. Holography, information leaves on the edge. Black hole thermodynamics teaches a surprising lesson. The entropy of a black hole scales with the area of its horizon, not the volume it encloses. This inspired the holographic principle, the notion that the information content of a region can be encoded on a boundary. In certain cases, this is more than a metaphor. It can be made precise as an equivalence between a gravitational theory in a volume and a non-gravitational theory on its boundary. If early universe physics admits a holographic description, then questions about violent beginnings might become questions about the behavior of a calmer edge. This perspective doesn't hand us a ready-made origin story, but it offers powerful tools to tame infinities and count information without losing track of causality. Horizons, causality, and the cosmic no-hair. Why is the universe so smooth on scales that would never have been in contact if expansion had always been slow? Inflation answers by putting formally separated regions into early communication and then stretching them apart. Cyclic and ekpyrotic models answer by letting a long, smoothing contraction do the work. In many scenarios, there is a no-hair tendency. Regardless of messy starting details, the dynamics drive the universe toward a simple, attractor-like state. That is great for explaining uniformity. It also means the earliest irregularities can be hard to recover. Our measurements must therefore focus on the fine structure of the leftover ripples, where small differences between models can survive the wash. The arrow of time, why memory points backward. The future feels open, the past fixed. Milk swirls into coffee, never the reverse. This asymmetry, the arrow of time, tracks the growth of entropy. But the puzzle of puzzles remains. Why was entropy astonishingly low near our beginning? Without that special condition, no stars, no chemistry, no memory. Some researchers treat a low entropy past hypothesis as a boundary condition. Others try to derive it from dynamics in a pre-bang phase, from constraints on initial quantum states, or from deep principles relating gravity and information. Any credible origin model must face the entropy question head-on. A tidy universe does not arise from a messy start unless the rules make tidy typical. So do they. Black holes, information, and the early universe. Black holes are laboratories where quantum theory and gravity dance uncomfortably close. They radiate, they evaporate, and the bookkeeping of information becomes delicate. Insights from these systems echo in cosmology. If information is never truly lost, even as horizons form and fade, then the early universe may also obey strict rules about what can be forgotten. Some proposals link cosmic initial conditions to quantum extremal surfaces, entanglement wedges, and other information-theoretic structures born in black hole studies. The technicalities are heavy, but the moral is crisp. The origin puzzle is not only about matter and geometry, it is about information and how nature stores it. Quantum measurement, records, and why observers matter, but not magically. In quantum mechanics, outcomes that leave no records might as well not have happened. Decoherence, interactions with the environment, selects robust patterns that behave classically. In cosmology, there is no external laboratory. The universe measures itself through internal interactions that create durable records. That is why talk of observers can confuse. No consciousness is required to make the universe real, only physical processes that create histories. Still, the reminder helps keep our language sane. We are reasoning from inside a world where memory is possible. Models that make memory impossible also make our reasoning impossible, and thus undermine themselves. Simulation talk, a philosophical mirror, not a physical model. It is interesting to ask whether our world could be computed by some greater machine. It is also important to note that such talk by itself is not physics. Without predictions that outperform rival models, simulation is a metaphor that can sharpen our sense of what counts as evidence, but cannot replace evidence. As a rhetorical mirror, it is useful. As an origin theory, it remains empty. Respecting that line protects us from sliding into unfalsifiable stories. What the next decade can actually tell us. This is where caution gives way to excitement. Increasingly sensitive measurements of the CMB's polarization can reveal or constrain primordial gravitational waves. Surveys that map galaxies and intergalactic gas in 3D will test the fine details of the primordial ripple spectrum. Gravitational wave observatories will listen for a cosmic background with a unique frequency signature. Precise counts of light elements and sharper maps of reionization will further narrow the viable models. Each improvement trims the underbrush of speculation. The best news is methodological. Even without a final theory of T0, the universe keeps handing us data, and data has a way of humbling overconfident ideas. Common myths, carefully dispelled. First myth: the Big Bang was an explosion in space. Evidence favors an expansion of space itself. No center, no preferred direction. Second myth: before the Big Bang, there was literally nothing in the everyday sense. Our best language simply fails near T0. The honest answer is that we don't yet possess a theory that cleanly applies there. Third myth: scientists have a single, settled origin story. In truth, we have a family of models that pass many tests, and a work in progress at the deepest step. Fourth myth: if we don't know the absolute beginning, we know nothing. On the contrary, we know a great deal about the first seconds, minutes, and hundreds of thousands of years. Those chapters are tightly bound to observation. Being precise about where knowledge ends is a strength, not a weakness. What a successful origin theory must do. Any satisfying theory of the beginning, or of whatever replaced the beginning, will need to remove singularities without hand-waving, explain or dissolve the low entropy puzzle, reproduce the measured statistics of primordial ripples, fit naturally with particle physics rather than bolting on exotic ingredients ad hoc, and offer at least one observational target, bold enough to risk being wrong. Elegance helps, but evidence rules. A beautiful theory that avoids engagement with data is a beautiful story. A less pretty theory that meets the sky halfway deserves a hearing. 2 thought experiments to sharpen intuition. Imagine twin clocks riding a contracting universe toward a bounce. One clock sits in an ultra-smooth region, the other in a slightly messier patch. If the bounce amplifies differences, the post-bounce sky would betray that past. If it erases them, then only statistics survive. The precise distribution of ripples, not individual scars. Either way, there is something to measure. Now imagine a universe that inflates, but just enough to solve smoothness and flatness, without creating a large gravitational wave background. That universe would look like ours in temperature ripples but remain silent in polarization twists. A detection would favor one path, a non-detection, another. These are not idle games. They map to real instruments. A slow walk back to T0. As we zoom from galaxies to atoms, then below atoms to the restless vacuum, one impression grows. The cosmos is both generous with clues and strict with logic. Generous because it preserves ancient records in radiation, in nuclei, in the arrangement of galaxies. Strict because it refuses to let us leap from poetic metaphors to physical claims without paying the price of prediction. We are allowed to imagine bounces and brains, eternal inflations and holographic edges, but we are not allowed to declare victory until the sky nods back. Why the beginning matters for the middle. Origins matter because they load the dice. The density of dark matter, the slight imbalance between matter and antimatter, the amount of primordial helium and deuterium, the depth of the first gravitational wells, all of it flows from initial conditions and the mechanisms that set them. The chemistry of your body, the life cycle of stars, the architectures of galaxies are mid-chapter consequences of prologue pages we strive to read. Understanding those pages does not diminish meaning, it enriches it, replacing mystification with a clear-eyed wonder that survives fact-checking. The discipline of I don't know yet. Science advances by drawing bright lines between what is known, what is plausible, and what is merely possible. I don't know yet is not a surrender. It is a commitment to standards that keep us honest. 100 years ago, cosmic expansion was a surprise. 50 years ago, the CMB was young news. Today, precision cosmology is a mature field. It is reasonable to expect comparable surprises ahead. Some ideas will sharpen, others will be retired. Humility is not a mood, it is a method. A practical checklist for origin claims. When you hear a claim about before the beginning, ask, does it address the entropy problem? Does it reproduce the measured statistics of primordial ripples? Does it remove singularities with clean mathematics? Does it fit comfortably with the rest of physics? Does it propose a signature we might see in the CMB, in gravitational waves, or in large-scale structure? If the answer to these questions is mostly no, the claim belongs to late-night conversations, not to textbooks. This checklist is not gatekeeping. It is quality control. The human thread. We tell origin stories because we are time-bound creatures who care about beginnings and endings. The cosmos does not require our curiosity, but it makes room for it. That is already a marvel. The point of this tour is not to promote a single doctrine. It is to show how disciplined imagination works, constructing models, extracting predictions, and asking the world to answer back. The wonder is not fragile. It survives contact with numbers. If we ever get a unified answer, it will look like this. Picture a theory that blends the smooth geometry of general relativity with the probabilistic grain of quantum theory, taming infinities at the Planck frontier. Picture its predictions arriving as patterns in the oldest light, as a faint sea of primordial gravitational waves, as a precise fingerprint in the distribution of galaxies. Picture an arrow of time arising not from a miraculous decree, but from lawful initial conditions that make low entropy natural, not contrived. Picture a framework that nests comfortably with particle physics while leaving room for surprises we have not yet imagined. That is what success would resemble. Not a single sentence, but a web of checks that hold together. At T0, the questions that matter are not what came before, but how do before and after come to exist at all. We have traced cautious answers, inflation's rapid smoothing, cyclic bounces that turn a beginning into a transition, holographic edges that store information as area rather than volume, quantum geometries that trade singularities for bounces, arrows of time that ask entropy to explain itself, instruments that can actually decide among possibilities. None of these answers claims finality. All of them claim responsibility, the promise to meet the sky with predictions and to accept correction when the sky answers back. Perhaps we will one day sow quantum foam gravity, information, and time into a single finite story. Until then, we have something almost as precious, a method that transforms mystery into questions sharp enough to test, and a universe willing to be questioned